All right, so last class, right, we went over the concept of the inverse of a function, and one of the ones we looked at was the quadratic function. So let's go ahead and just do that one more time. Remember, when x is squared, the entire x value gets squared, including the negative. So -4 times the second -4 would be +16. Yep. So uh, okay, so again, the quadratic function you worked with very heavily in Math 2. Yeah, make sure you're on the 3.2 one, not the 3.3. So the thing we tried last class was when finding the inverse, right? We said that, okay, the inverse undoes the action of the function. So if the original function takes a -4 and outputs 16, the inverse will take the 16 and give you back the -4. Yeah, so again, for the inverse function, we just switch x and y. No, sorry, that's 4, not. Okay, and then we hopefully agreed that when you do the inverse, it's no longer a function, right? Because it fails the vertical line test. You can draw a vertical line that touches the graph more than once, which means that there is at least one x value with more than one y value. Right, so here the x value of 9 can lead to both -3 and +3. Okay, so again, we like when things are functions because that means that we know exactly how they'll behave. Again, if you think about a vending machine, if you push the same button twice, you should get the same output twice. You shouldn't get two different snacks or two different drinks or whatever. Okay, so we want to take this inverse, which for me is in blue, and make it a function. Okay, so what do we need to do in order for the inverse to be a function? Well, it may seem like this wouldn't be allowed because we're like completely changing it. But in order to pass the vertical line test, right, like only one of, sorry, only one of these 2 points can exist, right? Because if they both exist, then it fails the vertical line test. Same thing over here, right? Only one of these two, only one of these two. And in between also, right? Like only one of these 2 points is allowed. Okay, so we actually want the entire bottom half to go away. Okay, so okay, I'll put the whole thing back, but we're basically gonna want this bottom half to go away. Okay, now the question was, how do we adjust the original function? Okay, so in order for this bottom half to go away, what do we need to change about the original parabola? Uh, remove what, sorry? Yes, do you know which one?
The thing that's going to be reflected over y.
Right.
It was x. I'll be the one on the left.
Correct. So Beckett identified in order to not have this bottom half, since the graph is a reflection over y equals x, it is the left half which created the bottom half. Okay, so we need to get rid of this section. So that means that we want to get rid of all the x values that were negative. All right, so by getting rid of these x values on the original function, then the values here no longer exist. and what's left over is a function. Okay, so what we can write down below, how do we adjust the original function? We say we restrict the domain to non-negative numbers. Okay, so non-negative is not the same thing as positive, by the way. That's why we have to use the phrase non-negative. The only difference between them, well, maybe one of you can figure it out.
Zero.
Yeah, zero.
Neither positive nor negative.
Yeah, perfectly stated. If we just said only positive numbers are allowed, that would not be quite correct because zero is allowed. So yeah, non-negative means x is greater than or equal to zero. Thank you. Yes. Oh, was there a question? Oh, we'll talk about that in a second. Let's focus on today's lesson first. Okay, so what is this new inverse function? So remember, the original function is x squared, or y equals x squared as the equation. Okay, so last class we learned how to find the inverse algebraically, right? You switch x and y, and then you get the new y by itself. So to undo the exponent of 2, you would square root both sides. Okay, so the inverse of x squared is the square root of x. Okay, so that's the function we'll be focusing on first. This is the parent square root function, the most basic square root function. Okay, so yeah, our graph is a little bit crowded now because we graphed the original function and then the inverse and then we changed it. The only parts that are actually part of the square root function are 0, 0, 1, 1, 4, 2, 9, 3, and so on going, right? You could do 25, comma 5 and so on. Okay, so yeah, only this highlighted part is the actual square root function that we're focusing on right now. Okay, so the key features for this domain of the square root function, well, notice the graph never goes forever to the left, right? 0, 0 is the furthest left you can go, because if you were to plug in, say, -1, square root of -1 is not real. Okay, so we can't go into the negatives, but we can use 0 itself. Okay, so you do bracket 0, comma, and then you can go as far into the positives as you want. You can square root, 64, 100, even something that doesn't square root nicely, like, 68, you could still square root it. It just won't be a whole number. Okay, so you can go forever to the right. Okay, so yeah, if you look at our square root function, the left end is just a dot, but the right end goes forever. So you only have an arrow on one side of your graph. Range, what y values occur? Well, the y values are never negative. Remember, we crossed off this section. So the lowest y value on the whole graph is 0. And this end is pointing upwards. Okay, so you can hit every y value again from 0 to infinity. And 0 itself is an actual y value, so we put a bracket on it. Well, For most of the functions we've done, yes, like unit one polynomial, unit two rational, except for the EVs. Yeah, but this one is new. Again, the reason is like when you're polynomial, you just have like 3x cubed. You can plug in negative numbers for x. That's all fine. But when you have square root, right, we know square root of a negative would be imaginary. It would involve I. So yeah, that's why we do not have negative infinity to infinity this time. Interval of increase for what x values are you walking upwards? Okay, so again, you don't start at negative infinity because the graph doesn't go over there at all. So starting as far left as you can at 0, you are walking upward as you keep going towards positive infinity, right? So the whole time you're walking upward. Just a reminder, for intervals of increase and decrease, you never use brackets. You always use parentheses, whether it's infinity or a normal number. Interval of decrease, well, you're never walking downwards. Again, you always walk from left to right. So you're walking upward the whole time. You're never walking downward. Okay, so there's no interval of decrease. X-intercept, okay, the graph does have a point at 0, 0, so that's both an X and a Y-intercept. Roots, well, the graph just touches the X-axis once at X equals 0. All right, so just one root. Okay, and then lastly, the end behavior. Okay, so we can start the same way as normal, right? As x approaches positive infinity, which means as the graph continues forever to the right, you can see the y values are going upwards.
And that's it for the behavior.
Yeah, so it's a little different, right? Because normally the second half of the statement is what happens as x approaches negative infinity. Yeah, here the graph doesn't approach negative infinity, but we will state what happens as you go as far left as possible. Okay, so this is going to seem kind of, again, unusual, but the furthest left we can go is the x value of 0. So we will say, yeah, as x approaches 0, yes, the y values are getting closer to 0. Okay, so any questions about the key features of our square root function? Again, this is the parent square root function, just y equals square root of x. All right, then the next thing to do is to introduce some transformations. Okay, so again, we've done transformations before, translations, reflections, rotations. So because we know that the square root is the inverse of the quadratic, right, we can sort of base it off a quadratic. So we've learned in the past that vertex form of a quadratic is a parentheses x minus h quantity squared plus k. Again, hopefully this looks familiar to you, vertex form of a quadratic. HK is the vertex. Okay, so general form of a square root function will look like this. A square root inside x minus h, and on the outside plus k. Okay, so very similar, right? And that's not a coincidence. This is done on purpose so that a, h, and k do the same things no matter what function it is. All right, so you notice a is always a coefficient. It always multiplies whatever the type of function is. H is always on the inside, getting subtracted from x. and then k is always on the outside getting added afterwards. Okay, so again, we set it up so that a, h, and k do the same things. So if you remember what a, h, and k do for the quadratic, they'll do the same things here. Okay, but let's go ahead and do a little refresher, make sure we know what each of these things does. Okay, so yeah, let me show a little animation. Okay, so here's that parent quadratic function that we just saw, right? Right now, it's just the basic square root of x. But again, a can be various numbers. It could be 2 square root x, 3 square root x, negative square root of x. H on the inside, you could subtract something from x, and k, you can add something at the end. Okay, so let's start by varying a. Okay, so what happens if we make a 2? So in front, it's 2 times the square root of x. Okay, so you can see the change in the graph, right? Or what if a is 3? Or what if we make a negative, right? So what if a is -1 or -2? Okay, so you can see the various effects. Okay, so let me just go ahead and let a vary a little bit. All right, so yeah, you can see the various things that happen as a changes, right? The graph can flip upside down, but it can also get like vertically stretched or vertically compressed, right? Okay, so again, here's a is 1, or closest possible, right? So as a gets bigger than 1, you can see the graph gets vertically stretched. If a is between 0 and 1, we call that a vertical compression. It's like you squish the graph down towards the x-axis. Right? Anything between 0 and 1 is vertically compressed. Now, the second a goes negative, it gets flipped upside down. It gets reflected over the x-axis. Right? But then same thing. When a gets more negative, the graph gets vertically stretched in addition to getting reflected. Okay, so again, a controls vertical stretch, vertical compression, and also reflection over the x-axis. Okay, so all of those things are a. Now h. Okay, so what happens if you have square root of x minus 2, okay, or x minus 3, or x minus -1, which would be x plus 1. Okay, so you can see that as h varies, the graph slides left and right. So this is a horizontal translation. Okay, so h again translates left and right. Oh. Okay, and lastly k. Again, what happens if k is 1 or 2 or -5? Okay, so you can see k shifts the graph up and down. So k is what we call a vertical translation. All right, so let's go ahead and write down our summary of those things. Let me switch back. Sorry, 1 second. Okay. Okay, so first to translate the graph, H is the horizontal translation. Okay, this is always the tricky one because it's x minus h. So h is basically the opposite of what it looks like. And then k is going to be your vertical translation. Yeah, k tells you how many units you translated either up or down, right? If k is positive, you translate up. If k is negative, you translate down. Okay, in order to make the graph reflect over the x-axis, that happens when a is negative. Okay, so remember the x-axis is the horizontal one. So if you reflect over the x-axis, that means you're going like this. So you're basically flipping it upside down. Okay, and then lastly, in order to vertically stretch or compress the graph, that is still the a value, but now it's not about the positive or negative sign. It's about the actual number. Okay, so because it can be either positive or negative, we're going to describe this with absolute value. Okay, so if the absolute value of a is greater than 1, we say that it is vertically stretched by a factor of a. Or I guess absolute value a still. Yeah, you should never say vertically stretched by a negative number. We would separately treat the reflection and the stretch. Okay, on the other hand, if a is something between 0 and 1, or -1 and 0, then instead we say it's been vertically compressed. It's what is written on the screen right now. Sorry, that's spelled wrong. All right. So again, these are the same things they did for quadratics. A was vertical stretch, vertical compression, and reflection over the x-axis. Right? H was still horizontal translation. K was still vertical translation. Okay, so the next thing we want to do is make sure we know what a perfect square is. That'll be very useful for the next part. So let's define a perfect square. A perfect square is equal to an integer squared. Okay, so it's kind of a silly definition, right? I'm basically saying a perfect square is something squared. But the key word here is integer. So integer is a whole number or a negative whole number, meaning no decimal, no fractions. Okay, so we want to sort of be familiar with the first few perfect squares. Okay, so you don't need to memorize this list. You can generate it very quickly, right? So you just start with, okay, 0 squared is 0, right? 1 squared is 1. 2 squared, 2 times 2 is 4. Right? 3 squared, 3 times 3 is 9. 4 squared is 16. 5 squared is 25. And you could keep going, right? You could do 6 squared, 7 squared. Technically, you could go backwards, right? You could do -1 squared, but that negative numbers times themselves are still positive. Okay, so we really want to know the first few perfect squares. Okay, so again, just looking at our list, 0, 1, 4, 9, 16, and so on. Okay, that's great. That'll help you with the next part. Hmm? Is it about the current lesson?
Yeah. Well, this is the final exam.
Yes, Unit 3 is part of what will be on the final exam. Okay, so again, you can memorize this if you want, but if you don't remember it, you just, again, go through the first few whole numbers and just times themselves, right? That'll get you the list. Okay, so that'll be very helpful for the next part. Okay, so let's go and turn to the back of this handout, please. Okay, so now we're going to graph not just the parent function, but the transformed versions of it. Okay, so there's different ways you could do this. You could start with the parent function and then translate it from there. But we're gonna use a different strategy. Okay, so we know for any function, the way that you get the graph, right, is you make like a table of values. You pick x, you plug it in, and you simplify to get y. Okay, now most x values are not going to turn out nicely. Okay, so for example, normally 0 is a perfectly good number, right? What happens if you plug in 0? Okay, you do what's inside first, 0 plus 5 is 5. Then the square root of 5 doesn't really, it's an irrational number. It doesn't turn out nicely. So we would probably not want to use this number. Okay, so what numbers should we use? Well, what's the benefit of perfect squares? Well, one second. Perfect squares are easy to square root, right? The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. Square root of 9 is 3, and so on. Right? So that's why we went over the perfect squares, because if we can end up at a perfect square, then it'll be easy to square root. Okay, so here's our strategy. We can write it at the top. Set the inside of the radical. I guess we could say the inside of the square root. Equal to a perfect square. Okay, so for this first problem, the inside of the square root is x plus 5. Okay, so I said set it equal to a perfect square. Okay, our first perfect square is 0. Okay, so we're going to set it equal to 0. So set the inside x plus 5 equal to 0. Okay, and then now solve for x. So solving for a variable means getting it by itself on one side of the equal sign. So in this problem, to get rid of the plus 5, the inverse operation would be to subtract 5 from both sides of the equal sign. Okay, so x equals -5. So for lack of a better term, I'm just going to call it a good x value. Okay, good because when you plug it in, it'll simplify nicely. Okay, so for this problem, now that I've identified that -5 is a good x value, I will go ahead and calculate what is the y value when x is -5. Okay, so, right, you would plug -5 in for x. Okay, so you take the good x value, plug it into the given function. Okay, and again, the whole point is that the square root should simplify easily. So square root of 0 is 0, and then 0 minus 2 is -2. Okay, so our first point is at -5, comma, -2. Okay, and then just repeat for other perfect squares. Okay, so we've already set the inside of the square root equal to 0, the first perfect square. All right, now let's set it equal to 1. Okay, so again, we're not going to use 1 itself. We're going to set the inside equal to 1. Yeah, good. Okay, so -4 will be our next good x value. Okay, and same thing, substitute it into the function above. Not quite. Because when you square root, when you square root +1, it's still a +1. So then when you subtract the 2 at the end, you get -1. Okay, so -4, -1. Oh, I'm glad to hear that. Okay, so we'll do one more together. The next perfect square is +4, because that's 2 times itself. So now we set the inside equal to +4. Okay, to get the x by itself, we subtract 5 from both sides. Okay, so x is -1. Substitute that into the function. Let's see. So square root on the inside, -1 + 5 is 4. So the square root of 4 is 2, but let's not forget we still have to do the outside -2. So 2 minus 2 gives us 0. Okay, so when x is -1, y is 0. Okay, let's see if we can get one more point. So the next perfect square is 9. Okay, I'm kind of out of space. I'll just do it up here. When x plus 5 is set equal to +9. Okay, so that means that +4 would be the next good x value. When you plug 4 in, you get y is +1. Okay, so 4, 1. Okay, so we can see our shape of the graph now. Remember, with square root functions, you do not go forever in both directions. This end, you can't go any further left than -5, right? If you tried, say, -6, on the inside, -6 plus 5 would be -1, and then square root of the negative would be imaginary. Okay, so -5 is the furthest left you can go, so no arrow on that end. But we do draw an arrow to the right. Yeah, that was another point on the graph. Okay, so domain, right, it's no longer 0, infinity. Here you can go a little bit into the negatives. Even though you can't square root a negative, since you're adding 5 to x, x can be, as low as -5 and still not be a negative afterwards. Okay, so just looking at the graph, the furthest left it goes is -5. So domain would be bracket -5, comma, infinity. Range, okay, the lowest the graph goes is the y value of -2. And this arrow is pointing upwards, so you do go upward forever. X-intercept, okay, you can see the graph clearly crosses the x-axis at -1, 0. Okay, now what about the y-intercept? Well, it's somewhere between 0 and 1, right? But we can't tell exactly where, but we can do a calculation, right? We know the y-intercept is where x equals 0. Let's see. Let's do the actual calculation by substituting in 0 into the function. Okay, so on the inside, 0 plus 5 is 5. Okay, so I would prefer you to leave it exact rather than using a calculator to round it. Okay, so it looks kind of funny, but this is the y-intercept. When x is 0, y is the square root of 5 minus 2. Okay, and then lastly, interval of increase or decrease. The graph starts at the x value of -5. And sorry, we should specify this is increase. All right, we start at -5 and we walk upward forever, no matter how far towards infinity we go. Okay, so those are the key features. And then lastly, going back to the sequence of transformations. So remember, those are based on A, H, and K. Okay, so, the general formula, A square root x minus H plus K. So for this function, A in front is invisible 1. Okay, so it's positive, there was no reflection, and it's not bigger than 1, there's no vertical stretch, and it's not between 0 and 1, so there's no vertical compression. So when A is 1, none of those things happen. No reflection, no vertical stretch, no vertical compression. Now, H is the opposite of what it looks like. It looks like +5, but because it's a subtraction sign, it's actually minus -5. Okay, so H for this problem is -5. On the other hand, K is exactly what it looks like. So K is -2. Okay, so again, based on A, H, and K, we have our transformations. There was no vertical stretch or compression. There was no reflection. But because H was -5, that means that we translated 5 units left. Negative H values are to the left. And then the K value means that we also translated 2 units down. Okay, so do not say translate -2 down. That would actually be wrong. The down already takes care of the negative part. Same thing with left. The left takes care of the negative. Okay. So that first row is complete. Do we have any questions about the first example of graphing a transform square root function? Yeah. Okay. Go ahead and try the next few, please. So use the same strategy, right, to find the x values, set the inside equal to the perfect squares. All right, so go and take a few minutes and try this out. Okay, so looking at the 3.3 handout, the other type of function we're talking about today is called the cube root function. Okay, so that means you're starting with what's called the cubic function, x to the third power. Yeah. So here, when you substitute in a negative number, right, the cubed means you write it 3 times. So the first 2 negatives multiply to a positive, but then times that third negative makes the overall value negative. Okay, so most of these points won't fit. As exponents get larger, the numbers get big very quickly. Yeah, exactly.
It's not like a parabola.
No. So yeah, it's more of like a almost like a lightning bolt shape, I guess.
Right.
Okay, so yeah, the root of 0, 0 would have multiplicity 3, right? Because the exponent of that factor is 3. So remember we sort of said, oh yeah, the graph kind of like wiggles through the root. Mm-hmm. Okay, so now let's do the inverse. Again, inverse means you switch x and y. Okay, so some of the points overlap, which is fine. Um, so this one is more horizontal. Okay, so we started with, again, what's called the cubic function, y equals x cubed. We switch x and y. So to get the y by itself, we would do the inverse of cubing, which is cube rooting both sides of the equation. Okay, so yeah, this is called the cube root function. Okay, so on the first handout for today, right, we said, oh, you got to chop off half of the graph so that it's a function. But looking at this one, it's already a function, right? It already passes the vertical line test. So we do not need to restrict the domain. Unlike the square root function where you cannot use negative x values, here you can. R A R E. Okay. So doing the um, key features. So here the arrows do go forever in both directions. So the domain is negative infinity, comma, positive infinity. Range also goes downward forever and upward forever. Interval of increase. So starting as far left as possible, which is negative infinity, you are walking upward the whole time. So the entire graph is increasing, which means none of it is decreasing. You're never walking downward, you're always walking upward. You do have an x-intercept at the origin 0, 0, so that's also the y-intercept. Roots, again, the x value where y is 0 is x equals 0. And this time we can have a more typical end behavior. As x approaches positive infinity, as it goes forever to the right, the y values are going upward forever. But then the other direction, as x approaches negative infinity, meaning as you go forever to the left, the y values are going downward towards negative infinity. Okay. All right. So transformations of the cube root function, well, they're going to be exactly the same, except a cube root instead of a square root. Okay, so it's all going to be the exact same. Okay, so you can copy it down from the other worksheet if you want, but it's exactly the same. Okay, and then our graphing strategy is going to be pretty much the same also, but it's going to be for cubes, not squares. Okay, so what are our first few perfect cubes? Here we have to be careful because remember, negatives are okay. Okay, so -2 cubed, -2 times -2 is 4, times a third -2 is -8. -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is +8. Okay, so the first few perfect cubes that we will often be using, -8, -1, 0, +1, +8. Sorry, that again? These are just possibilities, but it'll most often be these because the next one after 8 is 27, which, will normally not fit on our graph. So, sure. I don't know. Ask Mrs. Fisher in the back. Okay.
Like 5 cubes, 100.
Yeah, it gets really big, really, really fast. Okay, so let's just go and look at the back. So I said that you can copy it from the 3.2 handout because it's the exact same. Okay, so yeah, the strategy for graphing perfect cubes, you set the inside of the cube root equal to a perfect cube. Okay, so take the inside of the cube root, x minus 3, and set it equal to, let's do -8 first. Okay, so to get the x by itself, we would add 3 to both sides. Okay, so 5 is going to be, oh, sorry, that's -5, my mistake. So -5 will be a good x value. Again, you don't use the +2 because that's outside the cube root. Okay, so let's go and see what happens when we plug in -5 into the equation. On the inside, -5 minus another 3 is down to -8. Cube root of -8 is -2. -2 plus 2 is 0. Okay, so -5 comma 0 will be a point. Okay, now set the inside equal to the next perfect cube. Okay, so now we want the inside x minus 3 to turn into -1. Okay, yeah, 2 will be the next good x value. Okay, so cube root of -1 is still -1. -1 plus 2 is +1. Okay, so 2 comma 1. Okay, keep going. Next perfect cube is 0. Okay, but remember, we're not using 0 itself. We are setting the inside equal to 0. Let's make sure. Yes, looks like 3 will be the next good x value. Okay, so let's find the y value. Cube root of 0 is 0. So yes, 3 comma 2. Finish. Okay. Yeah. Okay, and let's keep going. Next perfect cube is 1. Okay, so yeah, 4. Cube root of 1 is still 1. 1 plus 2 is 3, so 4 comma 3. Okay, and then I'm kind of out of room, but I'll see it over here. The next perfect cube is 8. So 11. Okay, so when x is 11, cube root of 8 is 2. 2 plus 2 is 4. Okay, so 11 comma 4 doesn't quite fit on the graph, but I'll just estimate where it would be. Okay, so from those 5 points, we can definitely see the shape of the graph, right? At first, it's very horizontal. It's nearly flat. In the middle, it's speedier. It's more steep. And then it goes nearly flat again. Okay, so again, it's like a sideways lightning bolt. All right, so it'll look something like this. Okay. So domain, negative infinity to infinity. Range, also negative infinity to infinity. X-intercept, you can see it cross at negative 5, 0. Y-intercept, you cannot clearly see, so you have to plug into the formula. Okay, you could take the negative out front. Remember, cube root of a negative, the negative moves out front. Okay, and then the entire graph is increasing from left to right. Okay, so one thing I want you to notice, on the graph, there's sort of like a center point, right? It's called a point of inflection, but you want to identify its coordinates are h comma k. Okay, so h is what's subtracted, right, from the inside, and k is what's added at the end. Yeah. So you see here, h is 3, y is 2, k is 2, excuse me. And then you can see that that center point is 3 comma 2. Okay, so yeah, actually, sorry, I forgot to mention this. Going back to the first handout for a second, it has a similar pattern, right? So for this problem, letter A up here, h was negative 5, k was negative 2, and that's sort of like the starting point of the graph. Okay, so that'll be a very quick way for you to make sure your graph is correct. Identify h and k, and then that's where it is. Okay, so questions on that one? No. Okay, so for the okay, so for the rest of this page, you can check it on Canvas, but I wanted to give you guys